Hello everyone. In this video, I am explaining 8087 Maths coprocessor block diagram. This is block diagram of 8087 Maths coprocessor and detailed explanation of every block we are going to discuss in coming slides. Now let's start with features of 8087. The first feature is 8087 is numeric data processor. Numeric means numbers. So it processes numbers. So obviously something that processes numbers means it processes maths. So 8087 is known as maths coprocessor, numeric processor extension or floating point unit. It was the first math coprocessor designed by Intel. So 8087 is designed by Intel and it is compatible with 8086, Intel's 16-bit microprocessor, as well as it is compatible with Intel's 8088 16-bit microprocessor. It is faster in calculation than 8086 microprocessor. Why it is faster? Because it has some strong instructions which are capable to process the calculations very fast. It is 100 times faster than 8086. Why it is so? What happens? Suppose you want to perform any complex mathematical operation by using 8086 microprocessor. There, for that operation, you have to write a long program. And hence, 8086 takes time to execute that program. But for the same operation in 8087, direct instructions are available and hence it is less time consuming, and that is the reason 8087 is 100 times faster than 8086 microprocessor. It can work on integer, decimals and real type of numbers. 8087 has its own instructions. We all know that 8086 has its own instruction set. Similar to 8086, 8087 also has its individual instruction set. The instructions are capable of doing complex arithmetic operations like addition, subtraction, multiplication, division. They are capable of doing logical operations like AND, OR, XOR, etc. They are also capable of doing trigonometric calculations like sine, cos, tan, or logarithmic operations like calculation of log, etc. Now, all 8087 instructions starts with escape code. Now, as we know that 8087 has its unique instruction set, every instruction of 8087 starts with code of escape. It is a 5-bit code, that is 11011. Now, what happens? Let's take an example. Here you can see that the 8086 microprocessor is connected with 8087 maths coprocessor. Now, what happens in this? Now, we know that 8086 operates in two modes, that is minimum mode and maximum mode. What is minimum mode and maximum mode? What is maximum mode? Whenever in a system there are more than one processor, then we call it as 8086 is operating in maximum mode. This 8087 is a maths coprocessor. Coprocessor means it is a processor which is connected to 8086, and hence in this system there are two processors operating simultaneously. So whenever we connect like this, it is said that 8086 operates in maximum mode. Now let's assume here the simple connections are shown. Now we know that in 8086 there is instruction queue. You can see here this is instruction queue of 8086 microprocessor. Similar to 8086, 8087 maths coprocessor also has its own instruction queue. Now, whenever we write program for 86 or 87, what happens? It is always a combination of or mixture of instructions of 86 and 87. Suppose this is normal 86 program. In between, suppose we want to calculate some logarithmic function. Now, for logarithmic operation, there is no instruction available with 8086. So here what 8086 will do, here it will write instruction for 8087 because 8087 has instruction for logarithmic function. Now it will calculate log, here it will calculate sine, and then again it will write its own normal instruction. wherein it doesn't need the instruction of 8087. In between, again, it needs, suppose it wants to calculate sine, so it will use instruction of 8087, because there is no instruction with 886 for calculation of sine. So program always consists of combinations of instructions of 86 and 87. Now how to differentiate 86 and 87 instruction? 87 instruction always starts with code escape, that is 11011, which is a 5-bit code. What happens when it executes the program? First processor has to fetch the instructions. So it will fetch instruction 1 like this, and instruction, the same instruction will 1 will enter in the queue of 886, or as well as it will also enter in the queue of 8087 maths coprocessor. Both 86 and 87 will decode this instruction. After decoding, if they find that this instruction belongs to 886, because this instruction belongs to 886, so after decoding, if they find that this particular instruction belongs to 86, then only 86 will execute that instruction, and 87 will treat that instruction as no operation instruction, and it will do nothing. Then it will fetch next instruction, that is instruction 2. Again same instruction will enter in the queue of 86 and 87. Again both will decode the instruction, and then again it will find out that the instruction belongs to 86, and only 86 will execute this instruction, and 87 will take it as no operation instruction and will do nothing. Then it will fetch next instruction, that is instruction 3. Both will enter in the queue, both will decode the instruction, and they will find that this instruction belongs to 87 because it is starting with escape code. So what happens? Only 87 will execute this instruction, and 86 will take that instruction as no op instruction. That means when we interface 87 with 86, both will fetch all the instruction, both will decode all the instruction, but will execute only their own instructions. 8087 architecture is divided into two groups. What are they? The first is control unit. What is control unit, or what control unit does? The control unit of 8087 handles all communication between processor and memory. In the previous diagram, you have seen that we have stored the program in the memory, and memory was connected to 86 and 87. So it was fetching the instruction from the memory, or it will fetch data from the memory, and all this data transfer is taken care by control unit of 8087. So this control unit is responsible for fetching instruction. You can see here receive and decode instructions. So receiving instruction, decoding of instruction is taken care by control unit of 87. It reads and writes memory operands. That means data fetching, reading the data from the memory, or writing data into the memory is done by control unit. This is just a data communication. Data transfer between processor and memory is taken care by control unit of 8087 maths coprocessor. It maintains a parallel queue. You can see here, this is a queue. We have also seen it in the previous operation, like 87 has a byte instruction queue, and which is a part of control unit. The next part of 887 architecture is numeric execution unit. You can see here, this is numeric execution unit. So what this numeric execution unit does, it handles all numeric processor instruction. So this numeric extension unit is responsible for execution of numeric processor instruction. Numeric processor instruction means which instructions? The arithmetic instructions like AND, OR, multiply, division, logical instruction, AND, OR, XOR, trigonometric instruction, sine, cos, tan, logarithmic operation like log, and data transfer instruction. The execution of all these type of instruction is done in numeric execution unit. Now, what else is there in numeric execution unit? There is 8 register stack. You can see here in numeric execution unit, there is 8 register stack. You can see these are 8 registers, 0, and this is 7, means it is 8 total registers which hold the operands for instructions and their result. So data required for instructions are stored in these registers, and it also stores the result of calculation or result of instructions, you can see. So what control unit does? Control unit receives all instruction for numeric data processor 8087. That means for 8087, all the instructions are fetched by control unit. Instruction involving register stack. Whatever instruction that needs the register stack are given to numeric execution unit. Whatever instruction needs this register stack are given to this numeric execution unit, while control unit executes remaining instructions. Now, what is instruction queue? This is operand queue. Operand queue is nothing but instruction queue. We have seen in the second slide what is the use of instruction queue. What instruction queue does? It fetches the instruction and keep it in the queue, and it decodes the instruction. So what is written? 8087 maintains instruction queue identical to that of host processor 8086. The way there is instruction queue in 8086 microprocessor, similar type of queue is also available in 8087 maths coprocessor. Any instruction having escape prefix. What is prefix? Prefix means whatever we write before the instruction. This escape is prefix that we write before 8087 instruction. Any instruction having escape prefix is decoded and executed by 8087. So what 8087 does, it fetches all the instruction, it decodes all the instruction, and if it finds that there is escape prefix, then it will execute that instruction. And what about other instruction wherein there is no escape code? So other instructions are ignored by it. That means it will consider that instruction as, or it will treat that instruction as no operation instruction. Now in control unit, there is control word. So what is control word? We have to write control word. As name suggests, it performs the controlling operation. It controls the operation of 8087 maths coprocessor. So there is control word register. We have to write control word, or user has to write control word in control word register. So what is the size of this control word register? It is a 16-bit register. What is the use of this control word register? It allows programmer to select required processing option out of available ones. That means user can use a particular control word as per his requirement. Control words. Now, how to write control words in the control word register? Control words are sent to 8087 by writing them into the memory location and having 8087 execute an instruction which reads in the control word from memory. So suppose user wants to control the operation of 8087, he has to write control word in control word register. How to write control word in control word register? First, that control word should be transferred to the memory. That means that control word should be stored in the memory, and then 8087 has to execute some instruction, and that instruction will read that control word from the memory and will store in the control word register. Understood? First, the control word should be written in the memory, and then 87 will execute some instruction that will read that control word from the memory and will store it in the control word register. So user cannot directly store it in the control word register. It performs rounding control and precision control operations. So this is a format of control word. As I said, it is a 16-bit register. This is 16-bit register from 0 to 16, 0 to 15. So there are 16 bits, and these 4 bits are just kept reserved, and there are different operations for different bits, and that I'm going to explain in the next or coming videos. Right now, just remember that there is a control word whose size is 16-bit, and it is used to control the operation of 8087 maths coprocessor. Next register is status word register. Just below the control word in control unit, there is status word register. Again, size of this register is 16-bit. You can see here, this is the format. Here flags are available and some other operations are there. Now, what is meaning of status? Status is just to know what 8087 is doing at present. So if some user want to know what 8087 or what is happening inside the 8087, then user can read the status word. And from status word, it can find out what is the situation, what is the condition of 8087, or what presently it is doing, which flag is set, which flag is reset, etc. But then how the user can read the status word? Status word is available in the control unit, but how to read this status word? To read the status word from 887, you have to execute an instruction which writes the status word in the memory, where you can read or check it with an 8086 instruction. That means first you have to execute an instruction, or first you have to you have to execute an instruction that will transfer the status word into the memory. First you have to execute some instruction that will transfer the status word in the memory, and then execute 8086 instruction that will read that status word from the memory. So first execute an instruction to transfer the status word into the memory, and then execute 8086 instruction to read this status word from the memory. This is how the user can read the status word. So this is the detailed format. I will explain it in the coming videos. Now next part of 8087 architecture is numeric extension unit. What is numerical extension unit? Instructions involving register stack are executed by numerical extension unit. As we know that there is a register stack. Whatever instructions needs this register stack are executed in this part of 8087 maths coprocessor. That means that instructions are executed by numeric extension unit, and remaining instructions are executed by control unit of 8087. It uses operands from register stack because these kind of instructions use whatever data or operands are stored in the register stack. Now, what is register stack? What is register stack? So this is register stack. 8087 has 8 80-bit numeric data registers. So register stack is nothing but it is a stack of register, means register kept one above the another is known as stack of registers. Registers kept one above the another is register stack. How many registers are there? So there are 8 registers from 0 to 7. What is the size of each register? The size of each register is 80-bit. Size of each register is 80 bit. So how many total bits are there in the register stack? So 80 into 8. These many bits are available. So this much of data we can store in the register stack. These registers operate in last in first out manner. Hence they are called as register stack. What is meaning of this? As I said, it is a stack of registers. That means registers are kept one above the another like this. So it is like a stack of plates. So when we keep stack of plates like this, so whatever plate we keep at the last, we take out it first. Similarly, this also operates in the same fashion. If is whatever data we stored at the end, that we have to take out first. So that is why it is written last in first out. That means suppose data is stored in register 0, register 1 and register 2. So this data, whatever stored in register 2 will be taken out first, provided 3 is empty, 4 is empty, 5, 6, 7 is empty. Suppose data is stored till 3, then whatever is stored at the end, that means register 3 will be taken out first. So it is last in first out. Whichever is entered first will be taken out. Whichever is entered last will be taken out first. First, like the stack of plates, and that's why it is said that it is register stack. Each register is 80 bits, so size of every register is 80 bit. So size of every register is 80 bit. The current top of stack is called stack top. What is meaning of this? Suppose data is stored in register 0, 1 and 2 and 3 is empty, 4 is empty, 5 is empty, 6 is empty and 7 is empty. So last data is stored at register 2. So register 2 is nothing but stack top. Stack top means top of stack. The way we keep the stack of plates like this. Suppose these are two plates kept like this. So this is stack top. So last data entered in whatever register we enter the data at last is known as stack top. Suppose data is entered till fifth register, then this will be stack top and this is said that it is ST0. Suppose data is entered till 6, then this register is ST0 and this is ST1 and so on. So that is what is written. The current top of the stack is called ST0. ST stands for stack top or simply ST, and subsequent registers are called as ST1, ST2, etc. 8087 has 3-bit stack pointer. What is stack pointer? It is a register. What it holds? It holds the address of stack top. What is meaning of stack top? You can see here there are 8 registers. So if we want to address this register, so how many bits are required? To address 8 register, we need 3 bits only. So how to address this register 0? By entering this 000 will indicate address of this register 1. Then what is address of this? This is 001 and this is 010. What is address of this? 301 and 1. So what is address of this 8 register? It will be 1, 1 and 1. What is address of this register 6? It is 110. So how many bits are required? Only 3 bits are required if we want to address these registers. So what stack pointer does? Stack pointer holds the address of stack top. What is the meaning of this? Suppose data is entered in this register, in this register, in this register and this register. All other registers are empty, no data is stored in these registers. So what is this? Register 3 is stack top because last data available is in register 3. So this is our stack top. What is address of stack top? Address of stack top is 011. You can see here this is address of register 3011 and this 011 will be stored in stack pointer. Why? Because stack pointer holds the address of stack top. Suppose data is stored till 7th register, then this will indicate stack top and stack pointer will hold 111, which is address of this register. When we initialize the 8087, then no data will be available in the registers stack, and in that case stack pointer will hold 000 because it will point out 0th register and stack pointer will hold this 000. When we initialize, when we reset 8087, then no data will be available and a stack pointer holds 000 indicating this is stack top. Now next register is tag word. What is tag word? This is tag word register which is just besides register stack and it is very much related to register stack. Tag register is 16-bit wide. So its length is 16-bit. You can see here from bit number 0 to bit number 15. Contents of tag register indicate status of each of 80-bit register of 8087. What this tag register holds? Tag register holds the status of these registers 0, 1, 2, 3, 4, 5, 6, 7. The status of these registers is available in tag word. How? For every register there are 2 bits, that is tag 0 indicates status of register 0. Tag 1 indicates status of register 1. Tag 2 indicates status of register 2. Tag 3 indicates status of register 3. For every register, there are 2 bits, that is bit number 0 and bit number 1 for register 0. What it indicates, suppose these two tag bits are 00, you can see here. If suppose these two tag bits are 00, what it indicates? It indicates that register 0 holds normal number, that is non-zero finite number. It is a status. It indicates the status. So if it is 0 0, it indicates that there is a finite number. If these two bits are 0 and 1, 0 and 1, it indicates that register 0 holds all zeros, all zeros, all zeros here, all 80 zeros. If this bit is 1 and 0, if this bit is 1 and 0, it indicates that there is special number available in register 0. And if it is 1 1, if these tag 0 bits are 1 1, it indicates that register 0 is all empty. All empty. That means register 0 is empty if it is 1 1. So it is about the status of register stack. Now let's say suppose for register 4, this is stack 4 position. If these two bits are 0 0, it indicates that register 4 holds normal finite number. If it is 0 1, it holds all zeros. If it is 1 0, it indicates there is special number available in register 4. If it is 1 1, it indicates that it is all empty. So when 8087 is initialized, tag word is FFFF. Why it is FFFF? Because when we initialize, all register stack is empty, and when it is empty, all tag words will be 1 1, that is FFFF in hexadecimal number. So it was all about block diagram of 8087 maths coprocessor. Maths coprocessor is just to provide the strong mathematical operations to 8086 microprocessor. 8087 is very fast because it has its own mathematical instructions. And when we connect 8087 to 8086, it is said that 8086 is operating in maximum mode because 87 is a coprocessor. It is not any other interfacing IC. So I hope you understood why do we use 87 and what, and also about the block diagram of 8087 maths coprocessor. So thank you very much. Thanks for watching.